probably sometime in the middle of the week or whatever, or be up to look at that.
Do we gotta sign a disclosure?
In the Philippines, don't they call everybody her?
Huh?
In the Philippines, they call everybody her. I work with a Filipino guy, and he calls
They
guys
cannot
and
get-
girls, he calls them
They
her.
cannot get the he and she right.
So they say her?
Yeah, I don't know, it's really a weird thing.
I thought that's what you were doing.
Well, it's in the Philippines, for some reason, they have a real hard time with the her and the him and the he and the she. So you're right, they
Just call them
refer to
her.
it as she or her or whatever, and it's weird, it's like, sometimes you're talking and they'll be talking about her, and then it's like,
It's a dude.
yeah. Wait a minute, I
They
thought we
get
were
mixed
talking
up with
about
women and dudes a
So
lot
do you
over
speak,
there.
do you speak Indonesian?
Huh?
Do you speak,
Asian? Oh,
Filipino.
no, Filipino?
there's three main languages. Well, there's like 170 languages over there. It's crazy. So there's the main true is Tagalog, which is called Filipino. But like if you're in Cebu or any of the southern half, they won't speak that at all. They speak Cebuano, which is Visayan or Visayan, whatever you want to call it. And then if you go further down to Mindanao, they've got some mountain tribes that speak one thing, and I mean it's just
It's crazy.
Um,
Like a
my
bunch of
my
Mexicans.
ex, she's
close to Spanish.
Wadi is not even, you can't even find a dictionary online. It's so, like it's like the Cherokee language or something, like it's not published anywhere.
That's crazy.
So they learn it, it's called their mother tongue, they learn it in school, but it's not written down. And they use a bunch of abbreviations, you can't decipher it, like you have no, trust me, I gave up on trying to figure out what she was saying. You can't, there's just no way to do it.
She's over there smiling, talking shit about it.
Yeah, I know. I know that. That's what, okay. Just real quick, a couple of touch points I want to make sure I remember to tell you about. Three-phase calculations, right? Single phase and three phase is kind of like one guy on a bicycle versus three guys on a bicycle, right? If I'm one guy on a bicycle and I'm going up a hill, I've got a lot of power when my foot is at the top of the pedal position and I'm starting to push down, right? I mean, that's where I've got the most force on my leg to push the bike forward. But I get down about 120 degrees, I got nothing. And I got nothing on this leg either because I can't pull up. I mean, I just got to wait for it to come to the top on this side and push forward finally. And the separation between those two pushes is pretty far. And that's why I have to stand up a little bit and push real hard, you know, that kind of thing. Well, that's single phase is kind of like that. The bands of power are spaced out pretty far apart. So it's not very efficient compared to three guys on a bicycle with three different pedals that each have a 120 degrees phase difference, so that there's always somebody at the top of their pedal position when everybody else has got no position or pushing power. Does that make sense? And so your peaks of power are a lot more closer together in a three-phase system than they are in a single phase, right? Mathematically, how do I make this work? Because what I'm saying is that a three-phase system is more efficient, so I get more wattage out of less amperage in a three-phase system than I do a single phase, right? So mathematically, I've got to figure out how do I express that so that I can do math for three-phase systems versus single-phase systems and know what the ampacity is going to be. So you guys know how to do single-phase because earlier we took a 5,000 watt or we did something that was some wattage and we divided that by 240 volts, right? That formula right there is a WAV formula where the watt is always the combination of the two at the bottom. Abe and Vic. Abe and Vic. I'm going to get the same amount of work out of Abe and Vic no matter what. And so if Abe goes out and parties the night before and comes in dragging ass, well, guess who's going to have to pick up the slack? And I'm still going to get a watt out of the pair of them. Does that make sense? So if anything changes in this circuit, it's these two, and they're directly proportionately opposite of each other. So if one goes down by half, the other one has to go up double. Okay? But they're always multiplied to get the top product, which is the watt. So in this case, now if I'm looking for this number, then I'm just basically doing the math where I'm taking that and dividing it by that bottom value voltage, right? So 5,000 watts divided by 240 volts would give you amps out of that appliance. 20.83 amps, right? So that draws 20.83 amps, and if it's a single phase 120 volt, then I've got one wire rated for 20.83 amps and a neutral conductor coming back. Or if it's 208 volt or 240 volt, then I'd have, actually it's 240 volt, sorry. It'd be an A and a B, so I'd have both wires, each one would be rated for at least 20.83 amps. Make sense? Now, three-phase systems, instead of doing the math the way we just did it, I have to do something right here. So instead of dividing that by 240 volts, I have to divide that by 240 volts times the square root of 3, which the square root of 3 is equal to 1.73. I know there's some other numbers there, but they don't really care about anything past the second significant digit on the PSI exam, so we're just going to leave it at 1.73. So, all right. 830.4, 359.84 is it? And what is this one? 412 point something? What's 240 times 415 up 2. These are the three numbers you need to write down in the back of your book somewhere. Because I'm doing a three-phase calculation, I'm really using those three numbers instead of 480 volt, 208 volt, or 240 volt. Does that make sense? When I'm doing the math down here, instead of, if this was a 240 volt three-phase system, right? I've got an A, B, and a C, all connected to this appliance at 240 volts. I can't do the math to tell the ampacity by just dividing that by 240 because it's going to give me the same 20.83 amps. That's a single phase value that's not as efficient as a three-phase value. So what I'm doing here is I'm going to take this 240 volts times 1.73 first so that I can get the efficiency of that voltage power
12.
into the calculation. Does that make sense?
Yeah.
So this 415.2 goes here instead of 240. So same wattage, 5,000 watts divided by 415.2. Oh, sorry, 5,000 watts divided by 415.2. 1204. So 12.04 amps. Now you think, wow, that's a whole lot different. That's like almost 60 to 45% less. But really, what it is I've got 3 wires at 12.04 amps each, right? So it's not really as big of a difference as you might think. We're still looking at 36 total amps versus 40.83 amps. You know, it's not that big of a difference if you think about the 2 wires in each one of the system versus 3 wires. But it's certainly less per conductor than it would be if I'm running just 1 wire or 2 wires. Make sense?
What's that, 830.4?
480 times 1.73.
Oh, okay.
So just as a quick note in the back of your book, write those 3 things down. That way if you're doing three-phase calculation 480 volt, you use 830.4, 359.84 for 208 volt three-phase systems, or 415.2 if it's 240 volt three-phase systems. Those are the 3 you'll see on the test, right? So if you have a three-phase calculation to do one of those 3. 480, 240, 208.
Okay, 208, 240,
Yeah.
480.
This is 40 volt. This is 208 volt. That's 240 volt.
I'm lost, huh?
Three phases. Yeah. I want to get this concept right here where I've got these faces, these peaks closer together. I want to get that efficiency built into my calculation, and that's how I do it. So I multiply the voltage.
So how did you get those numbers on?
I took-
240 times the 1.7.
Bingo.
Okay.
I'm sorry, I should have spelled that out a little more. I just kind of
That's
jumped.
3 phase. That's all for 3 phase.
480 volts times 1.73 equals that. 208 volt times 1.73 equals that. 240 volt.
Oh, no, but that's a delta system, though, right?
Huh?
That'd be a delta.
Yeah, the 240 volt three phase would be delta. Right? I don't know why they love 240 volt three phase on this exam, and I think it's because single phase or three phase you have the same 240 volt, same thing applies to 208 volt, but I think they do it just because they count on you kind of pausing for a minute going, it's a 240 volt three phase, but there's plenty of it out there.
The 240 volt was that 415.2?
415.2. Wasn't it 415.2?
Yeah, that's.
Just as a quick note, right? Just putting those back there. Anyway, if I'm doing three-phase calculation, now in some cases, you don't have to do this. For example, if I'm doing a three-phase motor calculation, I'm trying to size a wire. There's a table in the back that already has this built into it, so you don't have to do it again on that table, right? If I'm looking for the FLA or the full load run value of a motor, I'm looking at a table that's already got the three-phase system, numbers already built into it, so there's no extra math. It's already done. But if I'm dealing with an appliance that's 240 volt single phase or 240 volt three phase, the math is going to be different based off of this one extra step, okay? So if it's a three phase calculation, you have to do this to the voltage system or system voltage values first. and then divide it into that watts to get the value of your ampacity, okay?
And your single phase, you just do the watts
Yeah,
divided
just-
by the volt.
Yeah, straight across.
And 243 phase is common here?
I wouldn't call it common, but it's not unheard of. There used to be a lot of it in the
Yeah,
residential side, because they had 244, they had three-phase air conditioner circuits.
Yeah.
So they ran an open delta and they had a third leg just specifically for the units, but.
Yeah, they're all downtown, all the deltas are
Well,
mostly
there's,
downtown.
yeah, on commercial side, but there's still residential 240 volt deltas out there, in, Shoal Creek.
Oh, yeah.
And so, yes, Austin Energy
Yeah,
said
yeah,
something out
that's
there.
right. Right there off of,
First time I ever pulled a meter, there was a blue wire coming out, I was like, what is this blue wire for? And in residential dwelling, yeah, it's a delta. It's a stinger. They're older.
I've only seen like 2 of those, and it was over there off Shoal
Yeah,
Creek.
yeah.
But now they knocked it down and built some.
Have it?
Yeah.
It's just because of the heavy air conditioning.
Built it.
Alright, makes sense.
Yeah, but there's some safety issues and concerns, with that residential dwelling, so we're getting away from it mostly, but there's also a two-phase system out there,
Yeah, that's crazy.
which is really weird.
Yeah.
I haven't ever seen one in person, but I mean, I know that,
It's in the network. Are you talking about the one that's downtown on the?
no, I don't think they have any of them here.
No, they do.
They do?
I believe it's over there by the substation. I
Really?
believe. Don't quote me on that.
Okay, so I just wanna make sure I cover that with you real quick, okay? Reciprocal math. All right, earlier, I need to talk about continuous duty and then reciprocal math, so let's talk about that real fast. The code book's kind of weird. They have to come at things from a different direction than where we come from in the field. Let's talk about continuous duty first before I get into that. Continuous duty. Earlier I said the biggest enemy we have is heat, right? Because if we put a demand on a wire and we force it to dislodge an electron back and forth between atoms, molecules, not atoms, it's going to heat up. It's going to create heat, and that additional heat in that wire will even create more resistance than what was there before. And at some point, it becomes large enough that it can feed off of itself and becomes a thermal runaway effect. So, heat on a wire is a bad thing. Here in a minute, we'll talk about it in more detail, but when we have continuous duty, specifically by code, what we're trying to do with continuous duty is if we recognize that we're going to demand the maximum value of that conductor for a period of time that's a certain length, then we're going to try to preempt that and oversize the wire so that it's not quite to the limit it would have been otherwise. So instead of running a number 12, for example, maybe continuous duty will make me run a number 10. So number 10 is going to have more area for that same value of ampacity to flow on, and it won't create as much heat, and might not even become a problem, right? How do I do that? I'm going to use a value of 125%. Basically, an increase of 25% in my load calculation and the size of the wire to that additional load value. That way, I'm forcing myself to oversize the wire effectively so that it's a little bit larger, so it can handle that same amount of continuous duty. Remember, continuous duty, we looked at that earlier, is defined as 3 hours or longer of the maximum available, maximum value of ampacity. So 3 hours is the magic number. In this test, on this test, if they give you a load that's obvious that it's continuous duty and there's no way that it couldn't be, in other words, it only has to hit 3 hours one time in its entire existence to be classified as continuous duty, right? There's not a commercial light ever invented, no matter where you use it, that you couldn't call continuous duty, right? Sign light, outside sign, security lighting, inside building light, bank lighting, things of that nature. I mean, every type of lighting you can think of in a commercial building would be considered 3 hours or longer continuous duty. And I don't think they could tell you that it's not. I almost would say that they told me it's not continuous duty, but it's lighting for a commercial building, I would still use 125%. You can't tell me it's not going to be continuous duty if it's obvious by what it does that it will be continuous duty, right? All right, same thing with motors. Motors are considered continuous duty for the most part, unless they tell you it's specifically not. And so there are other duty types. So continuous duty is just one of the duty types, which I think we looked at earlier, or intermittent, varying duty, periodic duty, so on and so forth. So there's some other types of duty that aren't 3 hours. Some of them are just on and off, whatever it might be. Okay, short time duty, so on and so forth. All right. Everybody understands what this 125 is. So if I had a 20 amp load that was continuous duty, I would multiply that times 1.25, which would give me, what, 25 amps?
Somewhere in there.
I would size the wire based off of 25 amps, not 20 amps, because of that continuous duty. That would make me run the number 10 instead of number 12, and so, there we go.
Unless it's a motor, right?
Hmm?
Unless it's a motor.
At new motors, we consider continuous duty, right? Unless it's all, like for example, a dryer, right? I know how a dryer operates. I know it's gonna be on for 30, 40, 90 minutes at most, and it's gonna shut off. And I might be really fast, I have the clothes ready to go, and I open the door and swap them out and close the door fast. Still not considered continuous duty, because I stopped it even for a second. It's no longer continuous duty, right? And it's obvious by what that machine does that it will not be continuous duty under any conditions of use, because it's got a timer on it. I know that, you know that, right? So if you have a question that had to do with a dryer motor, I'd just do 100%. I wouldn't consider that to be continuous duty. But if that motor is generic and I don't know what it does, I'm gonna have to consider that to be continuous duty.
Okay.
This is apparent that it's not. All right. What if I had a 16 amp motor? I had a 16 amp motor, and I knew that motor was continuous duty. Do the math real quick. 16 amps times 1.25 is what? 20 amps, right? Okay. So I'm doing this 16 amps times 1.25 because this is continuous duty, right? And I'm gonna make this look like 20 amps, so when I size the wire and the breaker, that I've got the continuous duty calculation built in, right? How many of you guys have ever heard that you can't put more than 80% of a breaker rating on a breaker? Have you ever heard that before?
Heard it.
Is that a rule all the time? Absolutely not. They wouldn't make a 20 amp breaker if you put 20 amps on it. That's, I don't understand. Like in the Philippines, they make a 32 amp breaker, they make a 14 amp breaker, like they have all kinds of specific sizes because
Now
they
you
make
got-
them specifically for
You
that
got 5
value.
and 10 amp.
If they didn't want me to put 16 amps on that breaker, they would make it a 16 amp breaker, right? So the difference is though, is what do you do? Take 20 amps times 0.80, what do you get?
16.
16 amps, right? 20 amps times 0.80 is 16 amps. You see anything that looks kind of familiar there? It's the same math. But the breaker's not rated for continuous duty is what the issue is, right? Only where I've got continuous loads on a non-continuous duty breaker do I have to worry about that 80%, but it's either one or the other, it's not both, right? The rule isn't 80% always, because if I have non-continuous loads that are rated for 20 amps, I can put 20 amps on a 20 amp breaker. That's if they're non-continuous duty rated loads. Like for example, if I had some plug loads or something like that, they're general purpose and they can come on for a little bit here or there or whatever, those would be 20 amps on a 20 amp breaker all day long. That's why it's rated for 20 amps, right? The 80% rule is because you have continuous loads, and rather than doing this math up here, you want to do it on this side against the breaker side by reducing the value of the breaker to compensate for continuous duty loads. That's what you're doing. When you do that 80%, you're doing it because it's reciprocal math against the breaker versus the value of 125 for the load value, okay? In the code book, because they don't really know what loads you're gonna have, they don't really know that the 16 amp continuous duty load or whatever it might be, but they do know standard breaker sizes or 20 amps, whatever. They will tell you in the code book, you can't put more than 80% of a breaker rating if you're using it for a switch, right? Because that switch or that breaker is not rated for continuous duty, so they're building it in for you, but it's reciprocal math. The 80% and the 125 are the same exact calculation. If I take 16 amps times 1.25, I get 20, or if I take 20 times 0.80, I get 16 amps. The exact same movement. Okay? I just want to throw that out there.
How does that work out if you like have a 20 amp, you know, and you have a receptacle that's, or a piece of equipment or something that's using 16, but it's on a 20, but then there's two receptacles on and they have another piece of equipment that's like 10.
So you're talking about break circuit requirements, and there is that, right? And so I don't want to confuse that with the breaker rating that we're talking about. But what just to point out what you're talking about, if you look at 210.19, is it? No, 21 on page 85. 210.23 A. By the way, if you really want, you talk about big changes. We have a 10 amp circuit breaker now. Did you guys
Yeah,
know that?
that's what I was saying.
Yeah.
We got
Huh?
10 amp and a 5 amp as well.
Do they have a 10 amp wire?
Sorry.
Okay.
I guess it's mostly for like automated stuff.
Because what's the
Automated
purpose of
controls.
that circuit breaker? To protect the wire.
We got 18 too.
All right. Anyway, so on page 85, on yours maybe 86 or something, but it's 210.23A, excuse me, B. B1 B2, C, D. So branch circuit rating, if you have a cord and plug connected equipment not fastened in place, there's an 80% rule. So I can't exceed a branch circuit rating with a single piece of equipment not fastened in place that is more than 80% of the branch circuit rating. Okay?
So that's when the 80% will count?
But again, that's not a breaker calculation, right? This is a rating of branch circuit because of that one piece of appliance. Now, the breaker would be the value that I would use to then verify the maximum size of that one not fastened in place appliance, right? So I couldn't have more than a 16 amp non-fastened in place appliance on that branch circuit rated for 20 amps, is basically what that is. And then if it's fastened in place, it can't exceed 50% of the branch circuit rating, where it also has other places for you to plug into. So, for example, if I have this right here, there's only one place for me to plug in. That is called a receptacle. That's the definition of a receptacle. This is called a duplex because it's got two receptacles on the same yoke. But receptacles are individual, single places to plug into, right? What this says here is that if I have anywhere else for you to plug into, then I have to not exceed 50% of the branch circuit rating. So if I put this, that's different. If I put this, and I plug one piece of appliance that's fastened, like for example, a room air conditioner or a window unit, right? If I plug that into that duplex, then I could also plug something in right here, and that's what this is talking about. Then I can't exceed 50% of the branch circuit rating for that one unit that's fastened in place, plugged into that duplex. Make sense?
How?
So your AC unit can only be 10 amps.
That's low,
On a
man.
20 amp circuit.
On a 20 amp circuit.
Yep. Or 15 amps on a 30, whatever, right? Okay, that applies to mainly window units where I see it more often than not. You'll see that same calculation in 440, but it's also listed here. So it cannot exceed 50% of the branch circuit rating where lighting units, cord and plug connected utilization equipment not fastened in place, or both are also supplied. So a duplex would be that exact example where you could possibly put something else in. 30 amp branch circuits have an 80% rating rule, and in 450 have a rule that talk about unit, like what you can use. So only non-lighting units other than dwelling unit, permitted to supply fixed lighting units with heavy duty lamp holders, infrared heating units, or other utilization equipment other than dwelling units. So you can have a 50 amp circuit to supply cooking appliances fastened in place in the occupancy, or other than dwelling units, you can have them to supply fixed lighting units with heavy duty lamp holders, infrared lighting, or other utilization equipment. Larger than 50 amps shall apply only non-lighting utilization equipment. Okay? All right, I just wanted to cover that real quick.
Summary of branch circuit
Hmm?
tree required.
How are we talking about that? Oh, because the continuous duty, right?
Yeah.
So the continuous duty, the reciprocal math there, I just wanted to remind you, the reciprocal math is weird because, I mean, we're using 125% and 80%. You would think the reciprocal 80 would be 120 or something, right? But it's not, it's 125. So it's the same calculation. You just do it either against the breaker. So for example, if I had 7,000 watts, right, of continuous duty lighting, and they were asking me to figure out how many 15 amp circuits I would have to have at 120 volts, how many branch circuits would I have to have for that lighting? I can approach this two different ways. I can either do it from the load side, or I could do it from the breaker side. I don't care which. All right? So if I do it from the load side, this 7,000 watts right here is continuous duty. So to make that load larger, I would do 125% of that 7,000 watts. To compensate for the continuous duty, making the load look like it's bigger than it actually is. So 7,000 times 1.25, 8750. So this 8750 then would be a continuous duty load that's already got the calculation built into it, right? Then I'm going to take that and divide it by 15 times 120, which is 1,800.
Are you looking at how many watts or?
Yeah, to convert to VA, 15 amps times 120 volts would be how many watts?
Oh.
1,800, right? So each one of the breakers, each one of my breakers at 15 amps at 120 volts, I multiply that. Remember, we're doing that WAV calculation where I've got the amps and the volts on the bottom, right? So amps times volts, which is 15 amps times 120 volts, is equal to 1,800 watts. I'm doing that because my number here is in watts, so I'm just trying to get the same unit, right? So if I divide that by 1,800, and I'm going to use 100% of the breaker rating because I've already got the continuous duty built into this top number. Make sense? I don't wanna take 80% of the breaker rating and do 125% of this, cause then I'm doing the same math twice. Make sense? So, I'm gonna take 1,800 and divide it into that, 4.86. What?
4.86.
This number exists. That could be 4.0000001, and that'd be 5 circuits. Don't let that 0.5 get in your head, right? If I'm doing a minimum calculation, that's literally the minimum, and I'm always rounding a minimum up no matter what, right?
So you need 5 of them?
No, I'm glad you said that, because that's.
I know, because like, it's like all the way 5, so it just makes sense.
Think about it like this, if I had 4.0001 gallons of milk, and I needed to carry that home, I'd have to have 5 1-gallon milk jugs, wouldn't I?
Yeah.
I mean, I'm gonna have to have very little in that 5th one, but if I don't have that 5th one, I'm just gonna spill it out.
Or drink it.
Or drink it, one of the two. But I guess what I'm getting at is that always round a minimum calculation up to the next number, so it'd be 5 circuits. Okay? Maximum values, I don't care if it's 4.99999, it's gonna be 4. I'm gonna round maximum values down every time, so minimum up, maximum down, depending on what my calculation is, okay?
Maximum
Up,
up,
I'm
okay.
sorry, down,
Maximum down.
Minimum.
Up. Gotcha.
minimum up, maximum down. That's what I'm getting at.
And that watts times amps, how do you determine if you're doing the amps or the volts?
Say that again?
You were saying with that chart you drew with the WAV, how do you determine if you times it by the volts or if you times it by the amps?
So that's a good question. That little circle that I drew is a mathematical formula. So this circle, the line right here is a division line. So if I'm doing anything on the top, this is a multiplication line, this is a division line. So if I have amps and volts down here and watts up here,
Wait.
I can solve for any one of the 3 variables just by covering it up. And so like if I were to cover the volts up, I would take the amps divided into the watts. Or in the case of what we did, we were looking for the amps, so it's the volts divided into the watts would give you the amps, right?
Okay, cool.
Yeah, so if I'm going this way, from bottom to top is division. If I'm going bottom, as I did with this one, then it's that times that, gives you watts, gives you watts. So this 50 amps times 120. I could have taken that 8750 and I could have divided it by 15 and then divided it by 120. I mean, that works, right? It's just a little bit more cumbersome, I think, than just doing it together and then that way you can, anyway. At 1800.
That's the simplified Ohm's law, right?
Simplified Ohm's law, what it is, absolutely. Okay. Just remember, I'm either doing 80% of the breaker derated, the breaker's not rated for continuous duty, or I'm doing 125% of my load because the load is continuous duty, but it's the same math, right? I'm only worried about the continuous duty is what we're trying to deal with that 80% in most cases. Okay? All right. I feel like that was worth your time because that's going to be important to you. You know, another thing too is, you know, mechanics of a problem is the other thing. Like I was trying to tell the masters earlier, you know, remember the basics, right? That's the mechanics of your calculations. So I've tried to put together, I think a lot of times people get a vapor lock on math calculations because they just don't know how to get started, right? Once you get started or have some way to kind of remember how to do it, then you're off to the races. But that's what this little page here was for. It's kind of hard to read. But it's basically a cram sheet of all of the calculations that I could possibly think of on one page there. So after you go to your study time or whatever, you know, kind of take a look at it. It's basically every calculation that I know of that might be on your exam, kind of in a nutshell. It may or may not make sense to you. If it doesn't, well, then you're going to rewrite it in that section to make it more sense for yourself, okay? All right, we're going to do conduit field, okay? Conduit fill is really cut and dry. What I see problems with is people just getting too lazy with looking up values, and sometimes you maybe look up the wrong insulation type. You might look at possibly the wrong wire size or something. But every wire has a different insulation type, and based off of that area, a surface area, which is measured in inches squared, right? So a given conductor that has a 1.73 inches square surface area, that's what that measurement would be. So if that was a wire that had, you know, THHN insulation or something, you know, number 12, I could have, I'm not sure if it's exactly what it is. number 10, number 12, THN has a value of 0.0133 inches squared. So that single wire, if I were to cut it off and measure the surface area of that wire, that would be 0.0133 inches squared, okay? Conduit fill is always talking about the interior of a raceway, and so I don't know why, but to me, if you're using an inner diameter instead of an outer diameter, then every half-inch conduit should be exactly half an inch, right? I mean, how hard is it for somebody to take a half-inch die and build their raceway around that half-inch die? But they don't. For some reason, it's different. Every conduit type, even though it's both a half-inch, they're going to have a different area of value of fillable area, okay? So you have to look up each one based off the conduit type, and that's what you see if you look on starts on page 716 of your code book. It's a little weird because they have a table on the top that's not conduit. Actually, sorry. No, it's fine. This is actually a different table, but it starts the second table down on page. What page you have there? 716 on that. What do you have? 719. Same thing. The table on the top of the page there, whichever one you have, is not a conduit table. It's a single shot or one shot vendor table. We use it for vending radiuses, but we'll talk about that in just a second. But if you look at the table right below that, the second one on the page there, it says table 4. At the top there, it says 358 EMT, right? So EMT, a half-inch EMT. The way I'm going to use this table is I'm going to use either the 40% column that's in inches squared, which is the second column under that 40%, or 60%, which is also the second column in inches squared. So either one of those, but let's just say that I had a 3-inch conduit. So 3-inch EMT under the 40% column is 3.538 inches squared. 3.538 inches squared. What that means is that if I have more than 2 wires in this conduit, the interior of that raceway, I cannot fill it more than 40%. So if that's 40%, it's actually more than 40%. Do it this way. 50% and 40%. How's that? Okay? So what they're trying to say with that 3.538 inches squared is that that's the maximum amount of that area of the interior that raceway I'm allowed to build a wire. So if I had all number 12 wires, I would take this number and divide it by this number, which is the wire size in inches squared, and that would tell me how many of those wires I put in.
What size of conduit are you working with?
3-inch conduit, 3-inch EMT. There is. What's that?
No.
Yeah.
I don't
Now-
know why, I thought you said half-inch.
I think I might have said that first, and I apologize, but if you look at the IMC, which is on the next page over, the second one there, a 3-inch IMC is a different value of 3.169. Right? 3.169 inches squared. So my point is, both of those are 3-inch conduits. We use both EMT and IMC. They're pretty common, yet the interior fillable area between the two is different. Well, again, we're talking about interior diameters. You think they would all be exactly a half-inch, or in this case 3 inches or whatever, but they're not, right? So, and then, again, we're taking a percentage. Now, let's talk about the percentage. Go back a page, to page 715 or 19. The table number 1 at the top of the page, I'm sorry, page 718, sorry. Table number 1 is the table that tells me what percentage of allowable use I'm able to do, and it's based off the number of wires. It's a little table right there. 15. All right, so it's real simple. If I have one wire, just one wire by itself, I'm allowed to use, what is it, 53%? That's a pretty significant amount of value there. Now, if I put 2 wires in there, it goes from 53 to 31. Pretty significant drop, understand? Mathematically and geometrically, it's physically impossible to take 2 exact size circles and put it inside another circle and fill more than 31%. That's the math. That's why it drops so far. Physically, geometrically, you take 2 identical circles and put it in an outer circle, 31% fill is all you'll be able to get, period. Weirdly enough though, if I add a third wire or a third circle in there, it changes a little bit and I can get more fillable area out of it and I'm actually bringing it back up to 40%. So one wire 53%, two wires 31%, two or more. Why didn't I just say 3? Right.
Over?
Yeah, right, 3 plus.
When would there ever be one wire?
What?
When would there ever be
That's a
one
great question. When would there only be one wire?
Oh, near the utility?
What if I had a utility area, let's say I had an industrial area where I had some SO cord that had multiple wires in outer jacket,
Oh, okay, cool.
right?
Yeah.
If you look at note 9, over here to the right of the table, note 9 says that if you've got a multi-conductor cable, like a single jacket over multiple wire, SO cord,
Data cord, something like
yeah,
that.
machine tool wire, MTW or something, then you're allowed to calculate that as a single conductor.
That makes sense. Yeah, you run data pipe, you usually run when you want wire.
Yeah. So that's exactly what the purpose of that number one
And that is a
is.
massive question too, right?
It is. You're gonna see you're gonna have a conduit filled with their weird, off the wall stuff that is just like,
Like major diameter eclipses.
yeah. Huh?
So when you're using like that.
Or-
So really the only time, I mean, really that's a good question, is how could I have electrically, could I have a circuit work with just one wire? I mean, and the answer is I can't, right? I mean, it's only used for, if I'm doing, maybe if I'm pulling a ground wire or something, I mean, you could argue that maybe, but.
If they want in case. Yeah.
So when are you gonna do that, and it's just gonna be a sleeve at that point, though?
Right.
It is.
And it's gonna be certainly less than 53% of the interior ratio, but really where we're at usually is the over 2 wires, which is 40%. So most of the time, 40% fill is what we're talking about. Now, here's the thing to remember. We're talking about 40% fill as if it was water, okay? So we're talking about 40% fill, and we're saying you can't fill more than 40%. We're talking about if all of it was compact, squeezed together, and there was absolutely no space between the wire, which that's not how wire gets pulled into a conduit, does it?
No gaps.
So 40% is really after you put some spacing in the wire, and do little bends and want to push them apart from each other, probably closer to about 55, 60%. I mean, so from a physical standpoint, right? So 40%, if you use these tables and try to maximize your available number of wires in a conduit, you're going to get numbers that are just practically impossible to pull, because it's not really 40%. It's like I said, bigger, probably closer to 60, 65%. There's one more thing on here that's not listed on this table, and it's in note 4. And I love it because they said they were going to take the word nipple out. Did they? No, it's still there. Nipples right there. I can talk about nipples and not get in trouble. It says so right there. Nipples, tubing nipples, not including connectors. Maximum length not exceeding 24 inches. Between boxes, caps, so on and so forth, we're allowed to use those at 60%. So now that's actually a significant thing to note, because not only can we use 60% fill, but we don't have thermal derating 24 inches or less. So you can probably get a useful number there. But at any rate, 60% again would be as if those wires were all bunched together with no space between them. So really 60% is darn near close to 100% of the value of that pipe by the time you get them pulled in there with a little space in between them. So just bear that in mind. I think that if you've ever tried to pull a set of feeders off a set of plans, and you had to use a tugger, or you had to use a forklift with a rope on it or something to pull it in, it's probably because engineers learn this stuff in school, but they never actually had to install it. So they don't realize that a half-inch larger conduit would save everybody a whole lot of time and trouble. So I'm just going to tell you, don't go to the office on Monday and tell them, you've been doing it wrong all this time, but let me tell you how to do it. Because these values that you'll get doing it by the code book are really, really, really strict.
No one ever thinks the guys in the field have to do work.
Yeah, exactly. All right, so let's kind of walk through this real quick. I've got some slides. Let me find it real fast. Just before I go even further though, remember minimum are rounded up, maximum calculations are rounded down. 0.8 or larger. If you look on note 7 here, on page 715 or 718, note 7 tells you that if I'm doing all the same wire in a raceway, and my calculation comes to 0.8 or larger, I'm allowed to round that up to a whole nother conductor. So for example, if I were to do the math here of a conduit fill, and I've got wire that filled up 40%, and it ended up being the 5.8 conductors, or 5.8 is the math that I got. That 0.8 means that 20% of that last wire is in the no-fly zone, but 80% of it is where I'm allowed to be. And so that's a small enough number then that they can allow me to round that up to 6.
So you could add an extra conductor in there?
Yep, I can have 6, right? Now, 5.5 would be rounded down. 5.6, 5.7, all those will be rounded down, those will all be 5, max. So the 0.8 means that only 20% of that last wire is where I'm not supposed to be, and that's significantly small enough at that point to allow us to have it. So 0.8 or larger on a conduit bill is rounded up. Anything less than that is rounded down. The 0.5 stuff that you think of when you talk about rounding up or down, you know, we're used to that 0.5 being the I guess the decision point for us, only applies to calculations that have to do with appliances or service calculations of that nature. Other than that, you're probably doing a minimum or maximum calculation, which is not a 0.5 decision maker. It's actually a minimum or maximum calculation. Breakers.
That's the 0.5 or larger.
Only like if I'm doing a like range we were talking about earlier, that maximum or that major portion, which was 500, whatever that rounded up. So that is, that 0.5 does matter in that case, but usually 0.5 is not what makes me round up or round down. What makes me round up or down is whether that's a minimum or maximum calculation. All right. Real quick, before we get off of this and go any further, breakers. Guys ask me, well, how do you calculate a breaker? And the answer is you don't. Breaker's not calculated. We calculate the wire, that's right. The process is this: I take a load, or a number of loads, and I add those together, and then the next step is I size a wire for those loads, right? Depending on what number of circuits on that. After I size the wire based off the loads, so I have loads, some of them are continuous duty, some of them are not. The ones that are continuous duty, I do the 125%. The ones that aren't, I don't, right? 100% of those numbers. Add all that together, and that says, okay, I need this size wire for those loads. Make sense? Once I get that calculated and the wire size is done, then the next thing is going to be 240.6. I'm sorry, 240.3 is going to be, and then about 6 is going to be the breaker size. So I think it's dot 3. 240.
Page 123.
I'm on page 120. 120, oops, it's not.
Reconditioning
4,
equipment.
4, sorry, 4. It's on page 123, or page 124. Section B, it's at the very top left-hand corner of page 123. On page 124, it's where? Where do you have it? Top left-hand corner. Section B, yeah, this is right here.
Oh, okay.
So it's on the top left-hand side. In my case, it's on page 123. In your case, it's on page 124. But both of them are on the very top,
Okay.
top of the page there. So here's the rule. I size the wire, and then I round up to size the breaker. Anything that's 800 amps or less, that's the kicker. So 800 amps is what aids, except in B, I'm sorry. B, C's the other one. So 800 amps is basically anything to size the breaker, then I'm doing a wire size, and then I'm rounding up to the next standard size over thermal protection device based on the fact that it's 800 amps or less. Okay? Section 240.6, which is on page 124, is a table that has standard size breakers. And so if you look on that page, page 124, page 125, let's assume do what y'all's would be. Let's see right there, the table right there. I would put a line or maybe highlight 800 amps because that's the decision point right there. Anything under that, you round up. Anything above that, you round down. So anything over 800 amps is basically 1,000 amps up is going to be rounded down. If you go back to page 124, page 123, 240.4C, which is on the right underneath that section B, is where that second set is, and it basically says you can't have a feeder that's rated for less than the value of the breaker. In other words, if it's more than 800 amps, you have to round down. So 800 amps or less, round up. Anything above 800 amps, round down. Masters, there was a question about a bus that was rated for 1,599 amps. And they're asking what size service or what size main overcurrent protection device would you have to protect the bus, and the answer is what?
1,600.
15.
16 amps. No, 1,600. The answers that they gave you were 1,600 amps, 1,200 amps, 1,000 amps.
1,200.
It'd be 1,200, right? And that's because this is larger. Even though that's only 1 amp away from a 1,600 amp breaker, Because it's over 800 amps, you have to round it down. The next smaller standard size.
What
would be
do
12 volts.
you mean?
I'm saying, I was just gonna,
What do you mean?
round it up.
If you had a bus that was rated for 1599 amps, the breaker size for would be 1200 amps.
Because it's over 1,000.
Right.
Okay.
Over 1,000 round down.
Oh, that's the next breaker side, yeah, on the
Yeah.
chart,
Yeah.
gotcha.
Any breaker over 1,000, you gotta round it down.
Which, if you think about it, between 800 and 1,000, basically anything more than 800 amps all the way to 1,000 rounds back down to 800 amps. So 800
Yeah.
amps is good for
Yeah.
a big long range, isn't it? A big range.
That's
what
crazy.
it is. All right.
There's
There are
another
some-
one with the fuse too, another I believe.
Hmm?
Can't, I'll find it for you later, they asked about the class of the fuse or something, those.
So if you're talking about that, you're talking about the 16 gauge or 18 gauge, and that's a really good one to talk about, but we'll do that tomorrow.
Oh, sorry.
I think that's, and don't let me forget to tell you all about that. That is definitely something you might see. All right. I can get off the slide now. I just want to kind of talk about that, just overview. So I'm rounding down on maximums, up on minimums, 80% or 0.80 on conduit fill. 0.5 applies to appliance calculations like ranges and things, or service calculations only. Breakers out 800 amps or less, round up over 1,000 or over 800 amps, round down. On the calculations on continuous duty is 125% or 1.73 if you're doing three-phase calculations, just kind of a overall recap. All right. What in the hell was that? All right.
Hey, better that than porno signing off.
All right. Sorry about that. I was not expecting that at all.
I was quite offended by that music.
Was it? Hey. All right. If I'm dealing with conduit fill, I'm looking at 40% or 60%. Realistically, a little more like that. So I think that's kind of my point. Just remember that when you're doing these calculations, you may get numbers that you would never want to try to build, right? So the notes that we talked about, the table there, 31% being because there's only 2 wires. Anything more than that's 40%. That's generally what we have. The nipple rule has to specifically be given to you as a maximum length, and if it's more than 24 inches or not stated, then 40% would be what you'd use based off the number of wires in it. So the nipple rule only applies if it's 24 inches or shorter, and that's connectors included end to end, right? So if I had a 24-inch nipple with connectors on both sides, I'm actually over that amount. So really that would be probably 18 inches or so. Bare conductors, if you have a conductor that doesn't have a jacket on it, they tell you to use table 8. So let's look at that real fast. Table 5 is your wire tables. Table 4 is your conduit tables, table 5 is your wire tables. If you look on page 722 or 721, for example, table 5, every individual wire type based off the insulation value that it has a specific value. It's the center column that we use that matches up with inches squared. So if you look on page 721 or 725 or 723, even when the page says starts. It's the middle value or the middle column on table 5 that I'm using. I'm not really using anything else, okay? So it's the inches squared or the approximate area, the middle value there. So for example, THHN, I did that a minute ago, THHN number 12. If I'm looking over on page 721 for me, page 7, THHN, and you have to be very careful to make sure that you actually have the right row there that actually has it in there.
0.0133.
0.01, what did you say, 0.01?
You gotta make sure you get the right one.
Yeah, 0.0133. I will tell you, be careful with the zeros that are after the decimal. They're important, so don't lose those. The ones in front of the decimal, don't worry about writing them down. It's just 0.0133 for number 12 key. THHW, if you look at the top of the page, you see THHW with 14 gauge starts up there at the top, and then it continues to number 8, but then it stops and becomes RHH at number 14 gauge. And then it picks back up again a little further down the page. So you just have to be very careful that you make sure you're on the right row for whatever the installation type that you're looking for, because they do jump around quite a bit. So the THHW, which is what we were talking about, is actually number, THHW is what I said, well, no, that's a THHN. THHN was number 12, it's actually at the bottom of page 721. And then your XHHW, which is your common feeder type, is the next page over. Again, we're using just the middle column there.
And that number, that .0133, that's,
One single number 12.
that's the radius of it?
That's
Or
the
size
area,
of it?
surface area in inches squared of a single number 12 THHN conductor. Right, so if I want to know how many number 12 THHNs I can stick in a pipe, right?
Yeah.
Earlier we did a 3-inch EMT and a 3-inch EMT. If I have more than 2 wires, I'm allowed to use 40% fill value. So 3-inch EMT, 40% fill was 3.538, right?
What table was that one in? Did you find that?
Table 4,
3.538.
it's on page 716.
Take that number divided by the other number.
Yep. So this is the maximum allowable fill area of a 3-inch EMT. 3.538 under the 40% column. And I'm using 40% column because I'm gonna have way more than 2 wires when it's all said and done. I'm gonna divide that by that single number 12, THHN is what we were looking at. So divide that by 0.0133. How much?
Is that
How
really
much?
low?
You're crazy. Really? What'd you try to do?
That's a big conduit for that small pipe.
Yeah, that doesn't sound too far off the bat.
3.538 divided by 0.0133. 266.01. I'm gonna round that down unless it's 0.8, right? That is- I don't know, maybe so. I don't really, we'll see.
Or is it 26?
Huh?
Is it 26 or is that?
No, it's
266 in that 3-inch?
So you're going to
Number 12?
265 conductors here. Do you have a maximum conductor rule in the NEC?
Well, we do from the thermal standpoint. I mean, at some point, yeah, more than 9.
12 gauge? Yeah.
266
I
only.
think you're 40 days. No, I was talking the whole conduit.
Probably the whole fucking thing, yeah.
Oh, really?
Like you're saying, the 40%
For all
goes
reasons,
more
it's
than what-
because
what
they
they
say
say might be
when you start
26.
pulling
Yeah.
back the cables, then you start buttering up the insulation.
Yeah, there's no way.
When you get that wire loop.
Okay, now, I don't know if it's possible to put 266 wires in there
Probably
anyway.
not.
But remember, when we're talking about conduit, fill, we're only talking about the physical properties, right? Can we physically stuff it in there? In that case, every wire counts, no matter what it is. I mean, we're gonna count every wire that's listed, right? But it's just physical. Now, thermally, we may have some issues with putting that many in a pipe, but from a physical standpoint, that's what it says.
Because you would start your degrading at this point.
Yeah.
And you would not hit 260.
No, unless it's nipple, because you don't have to derate nipples that are 24 inches or less. Even a nipple.
It's got some massive junction of boxes going to the front.
Like 4 feet by 6 feet.
All right.
Tire wall.
Let's see here. I think that's, so I want you to make sure that you highlight, on page 716 or back to table 4, EMT is the first table. Make sure you highlight, there's 3 things that we need to highlight. It's gonna be basically the the second column, the 4th column, and the 6th column. Because you're looking at, the trade size, the 40% fill in inches square, and then the 60% inches square. Those are the 3 columns you want to highlight under the EMT table, okay? If I were you, I would take my pen, and on the left-hand side of the table, I'd put EMT really big in block letters in my big chief tablet handwriting, so that it's easy for me to see what that table is quickly, right? If you put EMT over on the left-hand side of that table, you can't miss it. ENT, FMC, let's see, and then IMC, which is going to be on the top of page 717, or in your case
720.
720.
721.
I would do the same thing for IMC, but in this case, I would, on the right-hand side, I would put IMC really big block letters. So that's EMT, right, EMT really big right there on the outside edge of the table, so that whenever you're flipping through there, you can see EMT right there, you can't miss it, right? You got it, that's IMC, no, that's, yeah, it sure is. Oh, yeah, you got it, gotcha, all right? I just, that's fine too, because that stands out, that looks good, okay? You get the idea, all right. Then highlight that, just so you gotta, just maybe put that highlight or something, just so it stands out real big. And then if you go, down the next page, I will also point out FMC down the bottom got cut off, so you really have a carryover. FMC, the flexible metal conduit down the bottom, and you've got that, half inch down the bottom. Well, it just got split, but it's still the same table. And then for the masters, just a quick note, under Article 356, which is liquid type, the LFNCA, put a note to yourself to see page 33.
Sorry, they, liquid
The L,
type.
yeah.
So FNCA.
Mhm. That's the type C.
Right under
A
IMC.
and Z right here, so just put a note, mine is page 33.
Yours, what, sir?
Mine is page 33, yours might be page 34, 35.
Yes, sir, 'cause it's on your
But
field,
basically, on that page, there's the definition of what A, B, or C type is, so that's basically what I'm getting at.
That FMC, that's not talking about like, MC or anything like that, right? That's something, so
This
it's
is-
without any kind of conduit, without any wire.
Greenville.
Just pop, simply conduit, right?
Yeah.
Okay, cool.
Flexible metal, hollow.
That's Greenville, isn't it?
That's what they used to call it.
The definition of the difference between A, B, or C type, it has to do with the interior of the liquid type. It makes it an A, or B, or C.
Oh, right here.
Yeah, it just basically defines what those are. So on the test, they'll give you the definition of whatever the liquid type they're talking about, and then you're basically trying to figure out which table to use, either A, B, or C, based off the interior.
So where's
That's a master's question. On page 718 for rigid conduit, which is the next table, that's Article 344. Page 718 or page 721. On page 721 of the new book, it's kind of down at the bottom. Same thing on page 718 is RMC, which is rigid conduit. Again, put the trade designation over there on the left-hand side of the page, or in your case, the right-hand side of the page. And then on page 719, or the next page, you have Schedule 80 PVC at the top and Schedule 40 PVC right below it. And again, you want to label those on the edge of the table real big so you can be able to see it real quickly here. Schedule 80 half inch is smaller than Schedule 40 PVC, so if you had both of them in the question, you pick whichever the ratio would give you a larger type, which is Schedule 80, just FYI.
They have a half inch in Schedule 8?
Mm-hmm.
Oh, PVC they don't.
All right, and then if you look again on page 720, 721, under table 5, okay, 723, moving on, that's gonna be your wire table. And so what you just highlighted in the table 4, the middle column of table 5 is what matches up in the same unit of measurements, which is the area in inches squared, okay? All right, let's try an example real quick and see how you can do with that. Let's say that we had a, let's try this one. 3.5 inch EMT, how many 250 KC HHW aluminum conductors could you put in there? I'm just curious, if y'all were gonna guess at that, a 3.5 inch EMT, how many 250 KC mills do you think you could put in there? Just off the top of your head.
350 KC mill and a one,
A 3.5 inch EMT with 250 KC.
maybe 5.
All right,
Say
so-
six.
What do you think?
I would say 4. 4 would be easy to pull.
All right.
And try to put 5 in there.
Do the math there and see what you think. In this case, your raceway is a fixed value, so you're gonna start with table 4 and find out what that number is, because that's gonna be your maximum limit there, right? Then find your wire type, and you're gonna wanna divide that into that other number.
15.
XHHW. Does it matter if it's aluminum or copper?
copper.
No,
No.
because we're talking about physical size, right? I mean, a 250 kc mill gold would be 250 kc mill, right? Thermally it matters, but from a physical perspective, it doesn't.
Eleven?
11 is what you got? So, what'd you get for the 3.5 inch EMT? What was the value?
4.618. Yeah.
4.618?
1.8, yeah.
And then for the wire,
1.3904.
when you did that math, you got 11.8.
12.
And so you rounded that down or up?
Oh.
Up, right? That's where the .8 comes into play. If they're all the same wire size and the same raceway, then you're allowed to round up to .8. So 12 would be the answer. Again, I don't know if it's even possible. To me, for sure, that sounds like it's just not even.
You're not doing it.
Huh?
You are not doing
Yeah,
it.
not if you're going around any bends or
If you have any, yeah,
not too many couplings would probably give you that.
you'd probably start popping couplings trying to pull that out.
All right, but
That's
you guys,
how I know.
but you guys get the idea, right? And so the only reason why I'm allowed to round it up is because it's all the same wire size, right? That's the only time that applies. It would, if I'm gonna mix the wire sizes, then there's no point in it, all right?
If you're mixing wire size, you just do the same math and then add them all together.
Yep.
What we pretty much did was the 3.5, you get it, for 40%, so you take that one.
Yeah, so
4.39.
All right, let's say if we had, the following set of wires where,
No.
this is probably more common of a scenario where you've got,
Oh, shit.
2 number 8s, XHWs, 6 number, 250 kc mill THWs, and a 3/0 THWN.
Yeah.
What size rigid ratio would you have to have if it's equal to a length of 19 inches?
So then you divide it by 250
No.
aluminum, right?
No, it was, the wire size was SCHW, so you have to go with wire tonight. And then it was 250. So
And then you divide it by that.
Yes.
And since it's over the 8, like you were saying,
Mhm.
round it up to 12.
There you go. Take a shot at this one. You got a little bit different wire sizes here. I will tell you, the other thing they like to do is they'll give you like 4 number 8s and 8 number 4s.
Yeah.
I need to be dyslexic, so if you run across that, just try to focus on the wire size first, get that value, and then go back and look and see how many you have of that wire size.
Really? 6 250s?
So your math should be shaping up like that. If it's not, you're either in the wrong row.
And can you go back real quick? I was working on one last number there. I didn't see what that last one, the three, one, three,
Used to be.
Well, the nipple is 19 inches.
You've been in this class for 16 years already. Jesus.
I've been in 3 of them, this is my 3rd one.
Well, so again, your numbers should look kind of like this when you're done. You're gonna have each one of the individual values, 0.0437, 0.3970, and 0.2679, and extend it out by however many you have each one of those types. So 0.0874, 2.382, or 0.2679 is the sum, and add them together to give you a total value of 2.737, right? Take all the wire, put them together, cut it off and measure 2.737. So I need a raceway that's got at least that value or more, so I'm gonna round it up. I'm gonna go back to EMT, and I've got the 2.737. I'm sorry, rigid.
I wasn't sure, so we went off of a rigid pipe on that one?
Yeah, rigid galvanized, rigid metal conduits, that RFC, yeah. So am I using 40% fill or 60% column? 60. Why?
Because it's less than 24 inches.
Yep, they told me that it was 19 inches long, so that's gonna be your allowance to do the 60% column. So, 2.737 would fit in a 2.5 inch conduit, of 2.919 would be the value there for that. Okay? So once I'm done with the number, right, I bundle up the wire together, I need a conduit that's got at least that amount of space or more, okay?
It'll be a 2.5, right?
2.5,
Another good example, using that same number, the 2.737, right? If they gave me a question where I had that same wire that was running in a Schedule 40 below grade and I stubbed up in a Schedule 80 to, as it comes up. If you look at table 352 for Schedule 80 and for Schedule 40, it'd be a different conduit size depending on which one of those tables you use, right? Because 2.737 would only go in a 3 inch if it was Schedule 80, but on the 2.5 inch, or excuse me, Schedule 40, 2.5 inch would be okay.
You go with small conduit, right?
That's right. So, or no, the larger conduit, right?
Okay.
Whichever conduit gives you the
Oh, so
bigger.
you use the largest
value.
conduit?
Well, yeah, and the 3 inch then would be the minimum size, right, for both.
Okay.
Makes
I didn't know
sense.
if you ever gotta go from small to big or whatever.
Yeah. So you'd have, basically the answer would be 3 inch, because the Schedule 80 would require a larger raceway for the same amount. Does that make sense?
Yeah.
I mean, you could use a reducing bushing in the field that you want, but I mean, on a test, you can just answer one or the other, right? So it's,
Start making, start making that question, sorry.
all right.
It's just complicated enough.
All right. If they give you something weird, so there's a bunch of master's questions where they're giving you like a single wire that's a 2 inch diameter or something, or surface area, 2 inches. There was at least 2 questions recently that somebody called me about. One of them was a 2 inch wire and the other one was like a 1 3/4 wire or something. They're basically giving you the surface area of a single conductor and asking you to size the raceway for it, right? I mean, it's okay. I don't really care what you're giving me. It's the same rule. It's the surface area of the total of whatever the wire is. If it's a single wire, then table number 1 says one wire is how many? 53%, right? So I'm just in a different column if I'm dealing with one wire. So if they give me a 2 inch wire, so they're saying this wire has a surface area of 2 inches, and I want to size an EMT raceway, right? Table 1 tells me I can use a 53% fill value for a single wire in a conduit. So I would go to EMT, and I'm looking for a value that's larger than 2 inches under the 50% column. Does that make sense? 2 inches would be 2.0. I need a 2.5 inch, just like you said. ZMT. That makes sense, because of 3.105? So, I mean, they can give me a bunch of weird stuff, but it boils down to the value of the sum total of the wire. If it's one wire, it's just gonna put me in a column, or if it's two wires, then I'm gonna be in the 31% column, right? So they gave you two identical, there's one, they have a couple of, Cat 5s in a pipe or something, and they give you the value of the jacket, or basically surface area for the combined assembly. And it would just be the 31% column if I have a pair of those, and the raceway, you remember, multi-wire conductors under note 9 allow them as, count as one single wire, right? And so if there's two of those, it'd be two wires, 31% column would be what I use. So don't let them throw you off your game, and remember the 0.8 value, as well, okay? All right, I think that's it. Let's, we've got, let's see, it's 4:30, is that right?
Yes.
So we
We're
have.
going till 6:30?
Huh?
We're going till 6:30?
8 is what I was thinking. We've got box fill, which is gonna be what we'll do right after break. And then if we can, I'd like to do wire and capacity today. Really, we need to get that done before tomorrow. So, let's take a 10-minute break, and when you come back, we'll do, junk box, box fill.
Yes, sir, I have a question. On that reciprocal map, wherever you said it's either 125 or 80% of the weight. Like for
No.
motor
Still
loads
you get
plus,
the sound.
motor calculations plus other loads, or you just
Like,
multiply,
you put the
like
side
after
here.
you get that first one.
So this could be, maybe this is like a 12 gauge, and this is, these are gauges of wire,
Would you
different sizes
multiply
of
those
it.
by 125% too, or would you?
It's individually.
Yeah, but then would you, for that regular size, would you?
How late does the course stand? I thought it was till
No,
4:30.
This one was 8 till 8.
Eight? Is it usually
No.
later?
Oh.
What is it, what does it say on the paperwork?
I
5:30?
had to get home at 11.
So the whole circuit 80% rule is not really applied. What we're talking about is the portion that's continuous duty. You're gonna take care of that with 125% by increasing that portion. But it's not 125% of all of it. And so what you're trying to say is that would I do that portion plus 100% and then do I do the 80%? But that's still double dipping. You're still, you know, I mean, the 80% for the whole thing would never come into play.
Okay.
Yeah, it's, so, non-continuous duty loads and continuous duty loads combined have to be done individually, because you're gonna increase just a portion that's
Yeah,
continuous
which
duty.
would be the motor, right? And that's continuous at 125%. And then all those others are just taking that 100 profits
Correct.
out.
Yeah.
Okay.
And then you
Okay.
use 100% of the breaker rating at that point, because you already got the continuous duty taken care of for the portion of the load that is.
Okay.
Yeah.
Thank you, sir.
Question?